So let's start. Why power matters? So it sounds obvious because we assume that we had something which is battery operated. We want it to last longer, but usually this is the wrong answer. Because, for example, in the car we are connected to the battery, or if we are connected to the utility. So why power matter? So the next answer is in data center, the bill of the electricity, which is also usually not the right answer, because in data centers, usually the majority of the electricity they pay as a one chunk of a bill for the infrastructure. So this is important, but not as important as people think. So in reality, in most of the cases, we are not talking about power saving. In most of the cases, the companies are talking about achieving maximum performance per power envelope. And this is totally different. In many cases, it gives you different algorithms, different approach, etc. And so in some cases, we do care about power saving. In most of the cases, we know what is the budget that we will to spend, and we are targeting to get maximum performance from this budget that we have. So in the world of general purpose, usually, again, people are talking about maximum performance per power. By the way, all the usage of a heterogeneous system, for example, is to extract the maximum performance out of the budget, because GPUs, for example, are much more power efficient than general purpose for certain operations. So they don't like to sell the power, but they like to get the more performance for the power. But power is very important for thermal. So now the question why thermal is important. And thermal is important because of two things. Thermal is important because when the chips start to be too hot, we start seeing a lot of soft errors. And it's very important because it can even melt the silicon, which becomes a permanent error. And this is start to be very interesting. Okay. So let's go for a little bit basic terminology, and again there is a huge mix in the terminology that people are using, because power is the amount of joules or watt or whatsoever that system or component consume at a certain point. Energy is power per time, over time. And what we really call power management, usually this is energy management and not power management. And this is a mixture that everybody is doing. So power is impact the thermal, not the power consumption. The energy impact the battery life or the bill, etc. But again, this is a mixture that everybody is using. So I will keep with the tradition. I will mix them both. But just be aware that although we are all talking about power management, power tools, power, we mean energy, and not the power usually. Sometimes we mean power, and then we need to apologize that this time we are talking about power. Okay, thermal also determined by the hottest point of the system. There is another confusion, because people are talking about the general power that impact the thermal. This is important for cooling. It is not important for the reason that I mentioned before, of the soft errors and the malfunction of the system. Because for this reason, what we really care about is not the average, but the hottest point of the system. And in real system, the average between the hottest points and the average can be even 10 degrees, which is huge. And one of the problems is that when we put thermal sensors many times, we miss the hottest point, because the hottest point depends on the software behavior, and if we will miss it, we may even melt the system, even though the average is okay. So again, these are the terminology that we need to take care of. And there are many other things like power delivery and which cause faults and so on, but I will ignore all this part, all these issues as part of this talk because the time is limited and some people want to reach the event at the evening, so I'll shorten my talk. Okay, so let's start with some power versus performance basic equation and theory. I'll do it very fast. I don't like to go into all the details. We can spend a lot of time here. But in general, when we talk about power or energy consumption, we need to break it into active and passive. And we know that there are different mechanisms that the active power, we usually control it by the DVFS, and the passive or the leakage, we control it by slipping modes, and there are different mechanisms to control the slipping mode. Again, these are two classes of solutions. Sometimes we combine them, but these are two classes of solutions. The active power, usually we said that it is proportional to the CV square F, and usually you find in the literature, and it is correct, that V and F are proportional, linearly depend on each other. So we said that the power usually is proportional to F cubed. And this is the assumption in many of the papers. Leakage is, in many cases, is proportional to the temperature, by the way, by cube. Usually we ignore it. I don't think that there is even a single tool that actually takes this fact into account. When you look on all the tools, either they ignore the leakage or they say the leakage is percentage of the of the power, or they are just constant that we add to the system, but this is...
So when you write power, you mean energy? It's energy?
No, here power is power. Here power is power, and I said that the energy is active, but this is the power component, and we change all the time. The next slide will actually elaborate on this point. This is a great question, which means that the next slide will answer it. So, there's another terminology that I should put here, that what is operational point. When you put on chips, usually there is a table, and in the table there are operational points. And for each operation point, they say this is the voltage and the frequency that work. Usually you change the voltage and the frequency together, and later on we'll show how you change it. The software can control it. You just write a number to some control register, and you choose the operational point and move it from one point to another. You cannot just change it randomly. Usually it should come with a definition of all the operational points, and you need to choose in what operational point you or the operating system you want to work. So this is the theory, and the theory is quite simple. So let's look on the reality, and let's focus on the power. And again, this is the power, not the energy here. And the first thing that we see, that power proportional to the capacitance multiplied by the V square F, but the capacitance itself depends on the activity factor. Which means it's not the capacitance of the chip, but the capacitance is the active capacitance, which depends on the behavior of the system. And this changes from moment to moment. This is the reason this is power and not energy, because the energy will be the integral of the power over the time, but the capacitance itself changes all the time. So people just at very high level, they say, okay, let's take the average, but we know average is average, but if we care about the phase of execution, and this is something that we do care in real-time system, it very, very depends in even this loop you are doing floating point or integer or vector operation or other things. And it very, very depends on the activity, so you cannot understand the power without understanding the software. And this is something that we see all over again, that doing good power management or understanding the power of the system, you need to do software, hardware, co-design. You cannot do a good power management just by looking on the hardware or on the software alone. You must understand both sides. Okay, so let's look on the V square F, where we said that they are linearly dependent on each other, which is almost true. It's almost true because when we look on the voltage, and the voltage usually for any chip can go from Vmin to Vmax. And Vmin to Vmax meaning that you cannot increase the voltage more than some threshold. And for each one of the points, there is, we said there is the operational point. That is operational point said for, if you want to operate in this point, you must have at least this voltage. So this is the best for you. Now, you can go down, you can go to this place. But here you cannot lower the voltage anymore. So here you keep the voltage the same and you just change the frequency. Which means that now if we look on the equations, what's happened is that below the V mean the power and the frequency, and if we assume the frequency is some connection to the performance, they're linearly dependent. While on this part, they are dependent on the cube of the F. And this is tremendously different than even if we change, if we compare what is better to play with the voltage or to increase power, we need to understand this picture. It is even worse when we go to CMP or multiprocessors, because in CMP, because we have many processors, so usually we found out that the operational on the recommended point is something like here. So very soon we are going to this linear place, and people in papers and many people are still using the V cube, although they are deep in this place, and then the calculations are not correct anymore. Yeah.
So frequency is 1 over the period of the clock?
Yeah. Of course.
So it's the clock of the chip?
Yeah. There's a whole theory how you change the frequency, and the frequency you can change almost every cycle, because what you are doing is that you are taking the base clock, and then you put it in a shift register, and you have a different outputs. And each output is related to different frequency. So now you take this selector, and just by changing the input, so you can change the frequency almost immediately. To change the voltage takes you much more time. So if you want to increase it, you need first of all to increase the voltage. It takes you time, and only then you allow to change the frequency. The other way, you can change the frequency immediately, and then you lower the voltage. But these are the techniques that we are using. Okay, so again, this is very important to understand when we design a system. And just recently there are chips that introduced this turbo mode. And what does it mean, turbo mode? The turbo mode means that when Intel or ARM or a company sell you a chip, they are committed to the frequency that when all the processors are running, it will not exceed that terminal point. So as I said, this chip can run, for example, 1 gig or 2 gigs, etc., meaning that on average program, when I run it with 2 gig, I will not reach the terminal point. Why? Because otherwise you will sue them and say, okay, you sell me a chip for 2 gig, but whenever I use it, it reduces the frequency to 1 gig, so you cheat me. So when they sell you a chip which is, for example, 2 gig, it means that this is the operational point when all the cores are active. We know that in most of the cases, only part of the cores are active, which means that they have huge thermal slack that they can use. So this is what they call a turbo mode. When you're not using the entire cores, you can increase the frequency below the spec because they are designing the chip so it can reach the Vmax and actually they work at that point. So they use this part, so they design a system that when you run with lower number of cores, you can increase the frequency beyond the operational point. By the way, in a paper that we sent recently, we showed that in many cases, it is not always smart to go to parallel systems because when you use a single core, you can, or a small number of cores, you can run them in much higher frequency. It gives you more performance. And when you go to parallel, you lose some of the performance because you need to lower the frequency. So this is something that, again, usually we ignore in designing systems, and mainly about the software hardware interfaces. Okay, I'm trying to do it very fast, and I'll be glad to extend it later on, and even though I'm not sure that I will have time to cover everything, so, okay. Software hardware interfaces, so in order software to control the power, as I said before, there is a table, and the operating system or the user, at the user level, it depends on the system permission, etc. Whenever you write something to this control register, there are mechanisms in the system that lower or fit the frequency to the power, etc. Actually, in chips like in Intel, there is a small controller, which is a processor by itself, that is in charge of taking care about all this power and frequency, voltage, and so on. So when you write to the register, this chip actually read this small part, read the new value, and then you know how to deal with the power regulator, etc., and bring the system to the right place. But from your point of view, you just write it to the register, and magically the system is balanced to the level that you like. Now the question is, this is true for power plant. When we look on chips, so we have different power plants. AMD, for example, put every core on a different power plant. In Intel, they put the last level cache in one power plant, and each one of the core and the caches are in another power plant. So you have a control register that control each power plant. Now, all the cores and all the caches and all the elements within a power plant are running at the same voltage and frequency. Unless you are using some virtual power plant that you keep the voltage and you're just playing with the frequencies, but then the benefit of doing it is quite limited because much of the power that you can earn is because of the voltage and not because of the frequency, and the voltage also impact some of the leakage, but this indirect I will not go into. So this is when you design your SOC, or when you design your system, this is a major question if you want to have a better power management, how you break your system, how you put the power plants, which gives you what is the flexibility later on of your software in order to control the hardware. So in theory, you want to put every single element like processor, caches, and so on in a different power plant because it gives you the best flexibility. In reality, this is not true. We have a paper that we wrote about it. What you really like to do is to have clusters, and for each cluster to have a different power plant, because when you break it to smaller places, you start losing performance, and you have also problem with the power delivery. So usually you need to break your system into larger chunks, but you need to remember at that point that now every chunk which means that you can all the chunk with all the processor put down or up, but you cannot control the individual parts. Okay. I'll skip it. I believe that people know about it, but in all the modern processors, in order to do a good power management, we have performance counters. Recently, some of the companies start putting power counters as well. There is a big question how to use them, but the user level can use them. And if you build your system, and if you want to optimize your design, so you need to architect the power and the performance counter so it will serve the software that you want to run. Because otherwise you will not have the information to control the system. So whenever you design your own system, you need to think about what is the software that you want to run on it, especially in the embedded system, and to put the right hooks inside. One comment is that usually you don't need to put both power and performance counters. Usually you can derive the performance numbers by using power numbers by using performance counters. But now the question how many of the counters you can operate simultaneously, but this is a different story. But usually in big company there is, for any new chip, there is at least one performance counters architect. You need to architect this part. This is a very, very important part if you want the software to be able to control in a good way the power of your system. Same goes for thermal, etc. Yeah.
So I had a PhD student working on this kind of things, and he got extremely frustrated, and at the end we kind of abandoned this because there were very few sensors. I mean, and there are only every sensor. You have one sensor, temperature sensor for the entire chip. You don't have temperature sensor per core. And then you cannot control, for example, you don't have access to control the frequency of different cores, of different...
First of all, let's take it offline, but the simple answer, is that the new generation of both AMD and Intel come with a very new methodologies, and they are much, much better than the old one. And yeah, when I worked in Intel, we had only 5 general purpose performance counters, and what you do in that place, you just run it, and every millisecond, for example, you switch from one set of 5 to another set of 5. So things like clock, you constantly, and the rest you switch. You swap the counters, and then you get the picture of the entire run. This is for general purpose. For embedded system, thing that we know. So there are a lot of conception about how it should work, but when we look at the reality many times looks very different than the conceptions that we had. A small story, one of the mechanism that we put 10 years back in the Intel was that to start cleaning up cache memories when we go to sleep mode. And my manager told me, we will do some 5% performance for saving power for this case. And we implemented this feature, and when we run it on real system, we got 5% performance. We didn't lose 5%, we got 5%. Why? Then we realized that usually when you go to sleep mode, you finish the work. So all the dirty data line that you have in the cache, you don't have them anymore. So if you replace them when the system has nothing to do, so it costs you nothing. But if you just keep it as in the past, when you start working again, only then you start replacing them, and then the replacement costs you about 5% performance. So even though we work in power management for a long time, we had this mistake, and this time it was for us because we got much better result, but this is something that you need to experiment all the time because you get a lot of surprises. Usually the question is how to extract maximum performance per given power. Again, this is different than what most of the people think about power management. We need a new software-hardware interfaces. What we have right now is not sufficient, especially for mixed criticality, and it is not sufficient for multiprocessors. We need to build a new infrastructure. The main difference is that we need more global information about what the system is doing, and it is not good enough to look on each processor, and the current mechanism usually do not provide us this high-level information which is needed. And again, hardware-software co-design is the key point. And I look on the way that we are organized in EMC Square, and we have the hardware team and we have the software team. Maybe we need to think more about collaboration between the teams and to see how the power management and the software co-located and how we can collaborate with each time. Again, I mentioned that there were the traditional way to partition the system to subsystem most likely need to be revised, and we need to find ways to isolate the subsystem from the requirement of the safety, etc., but still allow sharing of resources. This is something that we actively work on it right now. Okay.